discuss the addition of angular momentum of two angular momentum vectors leading to the calculations of Clebsch Gordon coefficients. However, before we do so, I would like to spend a few minutes on the calculation of the spherical harmonics that we did in our last lecture. Now, we had said that the y, L, m are the spherical harmonics. Now, as we mentioned that L takes the values 0, 1, 2, 3 etc., and for each value of m, L, m goes from minus L to plus L. So, let me consider the case when L is equal to 2. Then we had shown that y, L when m is minus L is proportional to sine to the power of L theta, and the phi function was 1 over root 2 pi e to the power of the m value is minus L. So, this is minus I L phi, and I thought I will spend a little time on calculating the calculation of the normalization constant C. So, this part is normalized because the spherical harmonics are normal. The normalization condition is that y L m theta phi mod square and integrated over theta and phi. So, theta is equal to 0 to pi and phi is equal to 0 to 2 pi, and then multiplied by sin theta d theta d phi. This must be equal to 1. Now, if we take the phi part, then modulus square of that is 1 over 2 pi. So, this square is 1 over 2 pi. So, 1 over 2 pi and the modulus of this is 1. So, from 0 to 2 pi d phi, this is equal to 1. So, we are left only with the theta part, and therefore, the normalization condition becomes mod c square sin 0 to pi sine of 2 L theta sin theta d theta. This should be equal to 1. So, therefore, we make the substitution here that let cos theta be equal to x, then minus sin theta d theta will be equal to dx, and sin square theta will be 1 minus x square, and when theta is 0, this is 1, and when theta is pi, it is minus 1, but there is a minus sign here. So, you get c square, I interchange the sign, minus 1 to plus 1, sin square theta is 1 minus cos square theta x square raised to the power of L, and this is just minus of dx, and I have taken care of the minus sign. So, this is dx is equal to 1. So, this is the normalization condition. This is the normalization condition, and if I carry out the integration, this is the normalization condition, and if I carry out the integration, I will get C is equal to 1 over 2 to the power of L factorial 2 L plus 1 factorial by 2. It is a little cumbersome formula. So, what I am going to tell you today is that if you do not remember C, the value of C, then you can easily calculate very easily calculate by brute force integration. So, let me consider the case when L is equal to 2. When L is equal to 2, so you get c square minus 1 to plus 1, 1 minus x square whole square. So, this is 1 minus 2 x square plus x to the power of 4 times dx is equal to 1. Now, this I can integrate immediately. The first term will be x. So, that will be so x minus 2/3 x cubed plus 1/5 x 5, and this is really very simple. From minus 1 to plus 1, this is equal to 1, and if you calculate this, then this will readily give c is equal to under root of 15 by 16. Okay. So, therefore, we get the normalization constant as c is equal to 15 under root of 15 by 16. Similarly, for L is equal to 3, mod c square, and you will have this now the integration minus 1 to plus 1, 1 minus x square raised to the power of 3 dx is equal to 1. So, I can immediately write the 1 minus 3 x square minus 3 x 4 plus x to the so on. Yeah, I can immediately expand it, and if I do this, then you will get c is equal to under root of 35 by 32. So, what I wanted to tell you is that in case you do not remember the value of the coefficient, then by brute force integration I can calculate the normalization constant. So, therefore, we had the relation that y 2 minus 2 and this will be under root of 15 by 16 sin square theta e to the power of minus I 2 phi multiplied by under root of 2 pi. So, this will be equal to under root of 15 by 32 pi sin square theta e to the power of minus 2 I phi. So, this then is the expression for y 2 minus 2, and then we had the expression that L plus y 2 minus 2 will be under root of j minus m, that is 2 minus 2 minus 2. So, that is 4 into j plus m plus 1, that is 1, and this will be y 2 minus 1, and this will allow me to calculate y 2 minus 1. So, y 2 minus 1 will be 1 over under root of 4 L plus y 2 minus 2, and we had derived the expressions for L plus and N minus, and we have L plus is equal to 1 over under root of 4 e to the power of I phi delta by delta theta plus I cot theta delta by delta phi, and you substitute the expression for y 2 minus 2, that is c sin square theta e to the power of minus I 2 phi, and if you work this out, then you will get y 2 minus, this is a very simple problem, into 15 by divided by under root of 2 pi. So, the final result will be, it is a very simple exercise, 15 by 8 pi sin theta cos theta into e to the power of minus I phi. You see, because m is minus 1, so therefore, it will be e to the power of minus I phi. There is one more thing that I would like to mention, that we could have equally well started from the fact that L plus y L L. Now, so this is under root of j minus m, that is L minus L. So, this is a null ket, this is 0, and therefore, from this we can write down that if I write L plus y L is C times C L f L of theta, and the phi part will be 1 over 2 pi e to the power of I L phi. This is 0. Then the phi part will be 1 over root 2 pi e to the power of I L phi, and using the operator representation of the L plus operator, which is given by e to the power of I phi, so on, one can find out the equation for f L of theta, and if one works out the details, I leave that as an exercise, then f L of theta will also come out to be sine to the power of L theta. So, please see that y L comma minus L is C sine to the power of L theta e to the power of minus I L phi multiplied by 1 over root 2 pi. Then y L plus L will be the same constant. Actually, there can be a plus sign here or a minus sign here, depending on the value of L. This is what I wanted to tell you today, and that this multiplied by same sin L theta, one same constant, but except for a sign 1 over root 2 pi, this will be plus I L phi. So, in the case of y 2 2, that is L m is 2, we will obtain the same expression for C, and it will be a plus sign here 15 by 32 pi sine square theta e to the power of I 2 phi. So, why do I say that there has to be a plus sign here? Because we always choose a plus sign for y L comma minus L, because when you calculate the normalization constant, you can either choose, because you calculate mod C square. So, it is always arbitrary within a phase factor. We always choose for y L comma minus L a plus sign, and then we operate this by ladder operators and calculate y L m by operating some multiplied by L plus y L m minus 1. And then once the sign is fixed, you can keep on calculating the spherical harmonics, and you will, if L is 2, you will obtain a plus sign here. However, if L is 3, then one can show that y 3 minus 3 is equal to 35 by 64 pi sine cube of theta e to the power of minus I 3 phi. You keep on operating the ladder operators, you get y 3 minus 2, and these expressions are given in any textbook, y 3 minus 1 and then y 3 0, and then y 3 1, y 3 2, y 3 3. So, if you get y 3 3 from here, you will get minus sign here 35 by 64 pi. This will be the same factor, but now it will be a minus sign here sine cube theta, but the phi part will now be plus I 3 phi. So, I have told you the recipe for obtaining all these spherical harmonics, it is just working out patiently. And if you use the L plus 1, then what you will get is, here you will get for m is equal to 0, this will be 2l plus 1 by 2, it will come out P L of cos theta multiplied by 1 over root 2 pi, and this in this particular case will come out to be under root of L is 3. So, 2 into 3 plus 1 is 7, 7 by 4 pi, and P 3 of cos theta is 5 cos cube theta minus 3 cos theta divided by 2. What I would request all of you is that you start with this expression, and use ladder operators to obtain y30, and then start with this expression for y30, use again the ladder operators and obtain this. You can do it in any order. You can start with this and use L minus operators repeatedly to get y30, then y3 minus 1, y3 minus 2, all of them will come out to be consistent. So, therefore, I have given you the recipe that for any value of L or M, let us suppose I want to do y4m, I want expressions for y4m. So, first I write y4m, y44 or y4 minus 4 will be plus c sine to the power of 4 theta multiplied by 1 over root 2 pi e to the power of minus I 4 phi. I can also write down y 4 will be again plus c, same constant, sine 4 theta 1 over under root of 2 pi e to the power of plus I 4 phi. And I can find out c either by using the expression or by brute force carrying out the integration, or I can start with this y 4 comma 0. So, this is L is 4. So, 2 into 4 plus 1 is 9 by 2 P 4 of cos theta multiplied by 1 over root 2 pi. Of course, I must know the value of c. I can start with either of these expressions. If I start with this, then I must operate this by L plus and then again by L plus, then again by L plus and get all these. If I start with this, then I can, if I operate this by L plus, then I get y41, y42, y43 and so on, and if I start with this, then I must operate by this. So, therefore, in summary, I have given you a recipe for at least small values of L equal to 0, 1, 2, 3, 4. You start with I have given you the recipe for calculating first the spherical harmonic y L comma L or y L comma minus L. You obtain that, you write down that, normalize it, and then use ladder operators to calculate all the other spherical harmonics. And once to start with it is normalized, all others will be automatically normalized. Why did we choose the convention that y L minus L has to be positive? It is just like that. We could have easily chosen y L comma minus L can be negative also. But once we have chosen the sign of y L comma minus L, then the remaining signs are automatically fixed by the use of ladder operators. So, this concludes the recipe for obtaining the spherical harmonics. We now continue our discussions on the addition of angular momentum. Now, for example, that we have this electron in the say p state. So, electron in the p state has an orbital angular momentum L is equal to 1, and then you have its spin angular momentum, which we discussed, which is equal to half. So, there are interaction terms, there is an interaction as we will discuss later on between the spin angular momentum and the orbital angular momentum, and this leads to an interaction term in the energy. And therefore, we define the total angular momentum J, which is the vector sum of L plus S. So, I will consider a more general case, and we start this by saying that we will be considering what is known as addition of angular momenta, and we will develop a formal theory for that addition of angular momenta. We will consider, and which will lead to the calculation of what are known as Clebsch-Gordon coefficients. Clebsch-Gordon coefficients. These are extremely important in any calculations involving atomic and molecular spectroscopy. So, we consider two angular momentum vectors J1 and J2. Now, by this we mean that we have J1x, J1y and J1z, and these satisfy the same commutation relation that we had discussed earlier, that J1x comma J1y is equal to I h cross J1z, but h cross is 1. Similarly, we have J2x, J2y and J2z, and they also satisfy the same type of commutation relation, that is J2y comma J2z is equal to y z x. So, J2x and 3 similarly other relation. We say that the components of J1 commute with components of J2. By that we imply that J1x, as you can see, J1x does not commute with J1y, but J1x commutes with J2y. We assume that components of J1 commute with components of J2, any two components. So, J1x of course commutes with J1y, commutes with J2y is equal to 0. J1y commutes with J2z. Any component of J1 will commute with any of the components of J2. So, we assume that. So, we assume that the components of J1 commute with components of J2, but of course, J1 itself has the satisfy this commutation relation. We then define Jx, the total angular momentum vector J, such that Jx is defined to be equal to, when I have 3 equal to signs, then it means defined to be equal to, this is equal to J1x plus J2x. Similarly, Jy is defined to be equal to J1y plus J2y, and Jz is equal to J1z plus J2z. So, we define Jx, Jy and Jz by these three relations, and we will now show that we will now prove that Jx comma Jy is equal to I times Jz. The proof is really simple. So, we write down. So, we first write down what is, let us do this carefully, Jx Jy is equal to Jx Jy minus Jy Jx. So, you see Jx is equal to J1, I would like to do this little patiently, J1x plus J2x multiplied by J1y plus J2y minus the same terms, but in the reverse order. So, J1y plus J2y multiplied by J1x plus J2x. Okay. Now, let me just brute force multiply. Let me just brute force multiply. So, you will have is equal to, please see, J1x J1y plus J1x J2y plus J2x J1y plus J2x J2y. And the second term will be minus J1y J1x J1y J1x J1y minus J1y J2x minus J2y J1x minus J2y J2x. So, you see now that J2x commutes with J1y. So, this term and this term cancel out. Similarly, J1 components of J1 commute with components of J2. So, this term will cancel out with this term. So, I am left with these 4 terms. So, this J1x J1y minus J1y, this is the commutator of J1x comma J1y plus the commutator of J2x comma J2y. So, this is I J1z plus I J2z. So, this is I Jz. So, I have proved that if the components of J1 commute with components of J2, then Jx comma Jy is equal to I comma Jz. Similarly, I can show, I will leave it as an exercise for you to show that Jy comma Jz is equal to I comma Jx, and you have Jz comma Jx is equal to I j y. So, therefore, the components of j x, the total angular momentum vector, also satisfy the same commutation relations, and one can show, as we had done earlier, that the operator j square, which is defined as j x square plus j y square plus j z square, this will commute with j x, this will commute, j square will commute with j y, and this will, j square will commute with j z. Therefore, j square, j x, j y and j z satisfy the usual commutation relations, and therefore, we can have simultaneous eigenkets of j square, which I write as j m, is equal to j into j plus 1 h cross square, but I assume h cross to be 1 j m, and j z j m is equal to m h cross get j m. I hope I have made myself clear that the components of the total angular momentum vector satisfy the same commutation relations, and therefore, we can again develop the same kind of algebra, introduce operators like j plus and j minus, and obtain simultaneous eigenkets of the j square and j z. The question is, what are the values of j and m? How they are related to j 1 and j 2? What I am trying to say is that j 1 square and j 2 square I know. So, what are the values of, what are the eigenvalues of j square and j z? This is an extremely important problem. Now, let me go back to j 1 square. Let psi 1 j 1 comma m 1 be the simultaneous eigenket of j 1 square and j 1 z. So, j 1 square sorry this is equal to j 1 into j 1 plus 1 h cross square psi 1. I will, when I give the examples, it will become clearer, and j 1 z psi 1 is a eigenfunction of j 1 z also. So, I write psi 1 j 1 m 1 is equal to m 1 psi 1 j 1 m 1, and similarly let psi 2 be the eigenket of j 2 square and j 2 z. So, psi 1 is an eigenket, simultaneous eigenket of j 1 square and j 1 z. Psi 2 is a simultaneous eigenket of j 2 square and j 2 z. Now, please see, j 1 square commutes with j 1 z, j 1 square commutes with all the components of j 2. So, it commutes with j 2 square and it commutes with j 2 z. So, these 4 operators j 1 square, j 1 z, j 2 square, j 2 z, they all commute with each other, and therefore, we can have simultaneous eigenkets of j 1 square, j 1 z, j 2 square, j 2 z, and those wave functions I denote by the product wave functions. So, I write this as psi J1 J2 M1 M2, which is really a product of the two wave functions psi 1 J1 M1 psi 2 J2 M2. This product wave function is a simultaneous eigenfunction of J1 square, J1z, J2 square and J2z, and the corresponding eigenvalues are J1 into J1 plus 1, M1, J2 into J2 plus 1 and M2. So, these are simultaneous eigenfunctions of J1 square, J2 square, J1z and J2z. So, this represents J1 represents the eigenvalue of J1 square, that is J1 into J1 plus 1. This represents the eigenvalues of J2 square, J2 into J2 plus 1. Eigenvalues of J1z is M1 H cross and eigenvalues of J2z are M2. Now, similarly, I leave it as an exercise for you to show. It is really simple, maybe I will show it slightly later, that the operators J square, J1 square, J2 square, J square and Jz, they also commute with each other. And therefore, one can form simultaneous eigenkets, which we will denote by phi function. So, phi, we will put a ket sign here, J1, J2, J and M. These are simultaneous eigenkets of the operators J1 square, J2 square, J square and Jz. Of course, I know J1 and J2, they may be 1 half or something like that, but what are the values of J? That we will find out in a moment. We still do not know. Now, let me give you an example, but before that let me mention that what is Jz? So, Jz is defined to be equal to J1z plus J2z. Now, this function psi J1 J2 M1 M2 is an eigenket of J1z and J2z, and therefore, it is an eigenket of Jz. So, these psi functions that I have written, maybe I should write a ket here. So, let me write this down, that Jz operating on psi J1 J2 M1 M2 is equal to Jz is equal to J1z plus J2z. For J1z it is M1 and J2z is M2. So, this is equal to M1 plus M2 times the same ket. So, this ket is also an eigenket of the operator Jz belonging to the eigenvalue M1 plus M2. Thus, we now know all the values of all the eigenvalues of Jz. Once we know all the eigenvalues of Jz, we can find out immediately the eigenvalues of J square, because I know that J square Jm is equal to J into J plus 1 ket Jm, and therefore, and the value of m goes from minus j to plus j. So, if you give me a set of values of m, then the maximum value of m will correspond to the value of j. Let me give you an example. Let me consider the interaction of neutron and proton, or proton and neutron, or something like that. Both are spin half system. So, J1 is equal to half and J2 is equal to half. Then we have M1 can take two values, plus half and minus half, and M2 can take also plus half and minus half. So, what are the possible values of m, which is equal to m1 plus m2? So, the possible values of m are half plus half, which is 1, half minus half is 0, minus half and half is 0, and minus half is minus 1. These are the possible value, all possible values of m, that is, these are the possible eigenvalues of Jz. So, the maximum value is 1. So, we must have j is equal to 1, but when j is equal to 1, m can take values 1, 0, minus 1. So, this value is taken, one of these values is taken, one of this value. Now, there is 1 0 which is left. So, you will have j will be equal to 0 and m is equal to 0. This is known as the triplet state, and this is known as the singlet state. Okay, I will come back to this in a moment, but before that let me give you another example. Let me consider the interaction of the orbital angular momentum with the spin angular momentum. So, there is an interaction energy which is known as the L dot S term. So, we have two angular momenta, J1 which is the small l, and let us suppose I consider the 2p state of the hydrogen atom. So, L is 1, and therefore, m will take 1, 0 and minus 1, and J2 is equal to S is equal to half. This is the spin orbit interaction, and then this is M1 and this is M2, which is equal to plus half and minus half. So, what are the possible values of m? So, please see 1 plus half, that is 3 by 2, 1 minus half, that is half, 0 plus half is half, 0 minus half is minus half, minus 1 plus half is plus half, minus 1 minus half is minus 3 by 2. So, the maximum value of m is 3 by 2. So, the maximum value of j is 3 by 2, for which we will have m equal to 3 by 2 half minus half and minus 3 by 2. So, this takes care of this, one of this, sorry, one has to be minus here and also this. And then there are two remaining, half and minus half. So, then j must be equal to half. So, m is equal to half and minus half. So, you have two states, 2 p, this is the total angular momentum 3 by 2, and it is a doublet because the s is equal to half. So, 2s plus 1 is 2, this is the 2s plus 1 and this is the L value, and 2 doublet p half. So, these are the j values, j is equal to 3 by 2 and j is equal to half. Finally, let me give you, I am sure by now you are all familiar with the algebra, but let me just give you one more example. Say j 1 is equal to L is equal to 2. So, therefore, m 1 is equal to 2 1 0 minus 1 minus 2. j 2 is equal to s is equal to half. So, m 2, the two values are plus half and minus half. So, let me write down what are the possible m values. 2 plus half is 5 by 2, 2 minus half is 3 by 2, 1 plus half is 3 by 2, 1 minus half is half, 0 plus half is half, 0 minus half is minus half. I hope I do not make any mistake now. Minus 1 plus half is minus half, minus 1 minus 3 by 2 is minus 3 by 2, minus 2 plus half is again minus 3 by 2 and minus 2 minus half. These are the all possible values, these are all possible values of m. Once I know the possible values of m, I take the maximum value, which is 5 by 2. So, j must be 5 by 2. So, if j is 5 by 2, then this is 5 by 2, then m can take 3 by 2, half, minus 3 by 2 and minus 5 by 2. So, I will have m is equal to 5 by 2, 3 by 2, half, minus 3 by 2 and minus 5 by 2. Then there are 4 remaining, the maximum value is 3 by 2. So, j will be 3 by 2, m will be 3 by 2, half, minus half and minus 3 by 2. So, thus if n is equal to say 3, n is equal to 3, then and let us suppose L is 2. So, that is the 3 d state, you will have j will be 5 by 2 and 3 doublet again d 3 by 2. These are the two states corresponding to L is equal to 2 in the hydrogen atom problem, when we discuss the interaction of the orbital angular momentum and the spin angular momentum. Now, let me go back to this slide. Let me go back to the case. I hope you now understand the algebra. So, we consider two spin half problems. So, we have 4 psi functions. Please see, the psi functions are psi j1, j2, m1, m2. So, let me write it down. So, J1 is half and J2 is half. Now, M1 can take half, 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 minus half, minus half, half, minus half, minus half. And then there are 5 functions. 5 functions are simultaneous eigenkets of J1 square, J2 square, J square and Jz. So, we have J is equal to 1. So, there are 4 or 5 functions. So, this is half half, J1 and J2 are half, this is 1 and so you have 0. So, m is 1, 0, minus 1 and then m is equal to j is equal to 0, m equal to 0. So, let me write it down again. So, you have 4 psi functions. So, let me write here psi half, 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 half. These are the values of J1, J2, M1 and M2. J1, J2 is the same for all the 4 functions. In fact, many people omit writing that. So, there are 4 such value functions psi, half, half and this is half minus half, psi, half, half, minus half, plus half and psi, half, half, minus half, minus half. Now, for the 5 functions, these are 4. So, 5 functions there are also 4 J1, J2, Jm. So, these are phi, half, half, j I said that can take values 1 and 0. So, when j is 1, m can be 1, m can be 0 and m can be minus 1. So, this is phi, phi, half, half. This half half is repeated everywhere. Zero, 0. Now, you see when m is equal to 1, m1 has to be half and m2 has to be half. So, this must be equal to this, and when m is equal to minus 1, then m1 has to be minus half, m2 has to be minus half, because this plus this must be equal to this. So, this must be equal to this, this must be equal to this, and this must be a linear combination of this and this, because m is 0 and here also m is 0, because m1 plus m2 is 0. So, this function must be a linear combination of these two and this function must be a linear combination of these two. So, you have, for example, let me omit this. So, phi 1 comma 1 will be equal to will be equal to psi, let me write the half factor, I will tell you why I require that. Now, I want to find out, I want to get to phi 1 comma 0. So, what I do is operate this by j minus. So, j minus will be under root of j plus m. So, j plus m will be under root of 2 and j minus m plus 1, that is 1. So, this will be phi 1 comma 0 is equal to j minus operator will be j 1 minus plus j 2 minus. So, if I operate, this is value of j 1, one has to do this very carefully, j 1, j 2, m 1, m 2, and you will find that when I operate this by j 1 minus, I have to worry about this. So, j plus m, half plus half is 1 and j minus m plus 1, half minus half plus 1. So, therefore, this becomes psi half minus half, and if you operate by j 2 minus, you also get this. So, psi half minus half. So, I get finally the result that phi 1 0 is equal to 1 over root 2 psi half minus half plus 1 over root 2. We will continue from this point onwards in my next lecture, half. These coefficients are known as the Clebsch Gordon coefficients. So, we will continue from this point onwards in my next lecture.